In this lecture, I'm going to continue discussing consequences from mean value theorem. And the first of them would be the one that we mentioned already briefly before I introduced the mean value theorem, and it's the following. So it would be formulated as a theorem. Suppose that we have a function f that is such that f prime of x is equal to 0 for all x in some interval ab. And then a consequence of that is that f is a constant on AB. Let's do the proof of this. So we can argue by using a contradiction. You can argue as follows. So suppose not, then that means that there exist actually two x's inside AB, x1, x2, both are in AB, and they're such that f of x1 is not equal to f of x2, right? That's what it means for the function not to be a constant. Okay, so then we're going to consider the interval x1, x2. What do we know? We know that, first of all, that the derivative of f is equal to 0 on the open interval AB. And if it is equal to 0 on the open interval AB, that means that I should be able to compute a derivative at all points of AB, which means that f is differentiable on the open interval AB. x1 and x2 both belong to AB, so that means that the closed interval from x1 to x2 is going to be entirely inside the open interval AB. So we just said, since f is differentiable on AB, because differentiable implies continuous, f is continuous on AB. And so therefore, f is going to be continuous and differentiable on the subinterval x1, x2 of AB. And so therefore, mean value theorem applies on the interval x1, x2. And what we have is that there exists a point C inside the interval from x1 to x2 such that f prime of C is equal to f of x2 minus f of x1 over x2 minus x1. And by our assumption, right, x1 and x2 are two different points. So x2 minus x1 is different from 0. And f of x1 minus f of x2 is not equal to 0, right, because f of x1 is not equal to f of x2. So that means that this derivative is not equal 0. And this, of course, is a contradiction because f prime of x is equal to 0 for all x in AB. Right? And so therefore we're done. Because this means that at all points of the interval of x1, x2, then f of x1 should be equal to f of x2, which means that f must be equal to a constant inside the interval AB. All right, so that would be a consequence number 1. To formulate a corollary number 2, we would need to introduce some or reintroduce some familiar notions. So what else can we deduce about the behavior of a function from its derivative, right? So we can find critical points where derivative is equal to 0. If the derivative is equal to 0 everywhere, we just said that the function must be, the tangent line is always horizontal, and if it is always horizontal, that means that your function actually is itself a constant. And another familiar notion is that if the derivative is positive, then we should be able to show that the function is increasing. The derivative is negative, we should be able to show that the function is decreasing. And so this is what I'm going to establish next, again, based on the mean value theorem. So let's write down the following definitions. F is, so this would be 1. F is increasing on the interval AB. Now, what does it mean that the function is increasing? It means that the value at x, which is to the right of the previous x, is going to be higher than a value at the previous x. So f is increasing on AB if f of x1 is less or equal than f of x2 for any x1 less or equal, in fact, just less than x2, where both x1 and x2 are inside AB, right? In this case, the function is increasing, and we can give a similar definition to a decreasing function just by changing inequality signs, right? So f is going to be decreasing on AB if increasing x will decrease the value of the function. So f of x1 should be now greater or equal than f of x2 if x1 is smaller than x2. Further two definitions, and actually this is 2 and not 1. Number 3, we can also distinguish the case when the function is strictly increasing, meaning that it never is going to achieve the same value again. So f is strictly increasing on AB if f of x1 is going to be strictly less than f of x2, again, for any x1 less than x2, and both x1 and x2 are inside AB. So again, strictly increasing means that you can never level off, right? So you cannot stay at the same value of f. You always keep going up, moving up. And likewise, we can define a function which is strictly decreasing, again by manipulating the inequality signs. So this would be number 4. F is going to be strictly decreasing if the sign here changes to the greater or equal. Notice that I'm not defining increasing and decreasing functions by specifying the sign of a derivative, right? It is incorrect. One reason is that I can have increasing or decreasing function, but it's not differentiable, right? So increasing and decreasing, you simply compare the values of the function at two different x's, and if you have a certain trend, then the function is monotone, increasing or decreasing. So you don't need the derivative to introduce this definition. Sorry. Rather, the statement about derivative is a consequence of these definitions and differentiability of your function. And so let's state these as a theorem again. Suppose that f is differentiable on AB. And then we have the following consequences. Number 1, if f prime of x is greater or equal than 0 on AB, then f is increasing on AB. Number 2, if f prime of x is less or equal than 0 on AB, then f is decreasing on AB. Number 3, and actually let me just recycle these statements. Change these to strictly greater and strictly less, then that would imply that all the statements about monotone increasing or decreasing are going to be strict statements. So strictly increasing and strictly decreasing here. Okay, so let's try to prove that. And you already know what statement we would need to use. So let's prove, I don't know. Let me change the numbers here. Let's prove number 3. And then the rest will be similar, and you can try to prove them on your own. And I might have assigned some of them in the homework. So let's suppose that f prime of x is greater than 0 on AB. Okay? Okay, so then let's consider any 2 points x1 and x2 both belong to AB to be such that x1 is less than x2. Okay? All right, so then what do we know? Because derivative, just like in the previous corollary that I proved, because derivative is positive on AB, that means that f is differentiable at all points of open interval AB. And if it is differentiable, it's also continuous on AB, right? So because f is differentiable and continuous on AB, it is also differentiable and continuous on this subinterval x1, x2. And then I can apply mean value theorem, right? Because if the function is differentiable and continuous, differentiable on an open version of an interval and continuous in a closed version of an interval, then mean value theorem implies that there exists a point C inside x1, x2 such that f prime of C, let me move this, actually let me write it in a different order, such that f of x2 minus f of x1 divided by x2 minus x1, that this is equal to f prime of C. And what I know about f prime of C is that this is a positive quantity, right? Because I assume that f prime is greater than 0 everywhere on AB, so this is greater than 0. Okay? And what I know about x2 minus x1, well, I know that x1, I chose x1 to be smaller than x2, so x2 minus x1 is also greater than 0. And so denominator greater than 0, ratio is greater than 0, so this implies that f of x2 minus f of x1 should also be greater than 0, or, which is the same thing, f of x2 is greater than f of x1. And now, because x1 and x2 were chosen inside AB arbitrarily, it follows that my function f is what? At a larger x, it will always have a strictly larger value, so that f is strictly increasing. And so we're done. Right, and again, the other three statements can be proved in exactly the same way. All right, so then in the next installment of a lecture, I will continue with these corollaries.